You ever stop to think about how your email just knows what's junk and what's important? Or how your credit card company can flag a weird charge, like, instantly? Well, the answer is this really powerful idea in data science called classification. It's all about teaching computers how to be expert sorters. And trust me, it's a skill that is quietly running the world all around us.
Just think about it for a second. Your email inbox, your credit card statements. Every single time an email lands, a computer has to make a call. Spam or not spam? Every time you tap your card to pay for coffee, a system is checking, is this legit or is it fraud? These are classification problems happening in milliseconds, over and over. And that's really just the tip of the iceberg.
But this goes so far beyond just daily convenience. Classification is being used in some really high-stakes fields. I mean, doctors use it to help tell the difference between benign and malignant tumors. Banks use it to stop fraud in its tracks. News companies use it to sort articles automatically. And scientists are even using it to understand the fundamental building blocks of life, like proteins. The applications are just massive.
So how in the world do we get a machine to learn this sorting skill? Well, it turns out there are two main ways to go about it, a real fork in the road for any machine learning problem. And understanding this split is totally key to everything that comes next.
Okay, the analogy here is just perfect. Think of supervised learning like studying for a test when you have the answer key. The data is all labeled. You have the questions and the right answers, so the machine learns by checking its work. Unsupervised learning, on the other hand, is like being handed a giant, messy pile of photos and just being told, sort these. You have no labels, no answer key. The goal is just to find natural groups and patterns on your own.
So for this explainer, we're heading straight down that supervised path. We're going to zero in on classification, where the whole point is to learn from data that already has the right answers so that later we can make smart predictions on brand new data the machine has never seen before.
All right, let's dive into our first model. It's called K-nearest neighbors, or KNN for short. I kind of like to think of this one as the social butterfly of algorithms. Why? Because it makes all its decisions based on the company it keeps.
And this quote? This is the entire philosophy of KNN in a nutshell. It's basically the data science version of birds of a feather flock together. The whole thing works on this really simple, super intuitive idea that any given data point is probably going to be in the same category as its closest neighbors.
Now, you'll often hear KNN called a lazy algorithm. But don't let the name fool you. That's not a bad thing. It just means it doesn't do a ton of heavy lifting up front to build some big, complex model. Instead, it just chills out, stores all the data it was trained on, and saves all its energy for the exact moment you ask it for a prediction.
So here's how it works, broken down into 4 simple steps. First, you pick a number, K. That's how many neighbors you want to ask. Let's say we pick 5. Then, when you get a new piece of data, you calculate how far away it is from every single other point. From there, you find the 5 closest ones, the K nearest neighbors. And finally, you just let them vote. Whichever category shows up the most among those 5 neighbors wins. That's the label your new data point gets. It's really that straightforward. So KNN is fantastic because it's so simple to get your head around and put into practice. But, and this is a big but, its lazy approach has a major downside. Because it has to compare a new point to every other point in the dataset, every single time, it can get incredibly slow if you're working with a lot of data. It's that classic trade-off. You get simplicity, but you might have to sacrifice speed.
All right, on to our second model, the decision tree. Now, if KNN is all about social consensus, a decision tree is more like a strategic flowchart. You can almost think of it like a game of 20 questions. It gets to an answer by asking a series of simple, targeted questions. So what is it really? A decision tree is basically a map of questions. You start at the very top, at the root, and you ask a question about the data. Depending on the answer, you follow a specific branch down the tree to the next question. You just keep doing this, going down and down until you hit a leaf at the bottom, which gives you the final classification.
And that, right there, leads us to the most important question of all. With all the possible questions it could ask about the data, how does the tree figure out which ones are the most powerful? Which question gets to be at the very top of the tree?
The goal is all about increasing purity. The best question is always the one that does the best job of splitting a messy, mixed-up group of data into purer subgroups, groups where, ideally, everything belongs to the same category. You want to move from a state of high impurity to one of low impurity with every split.
To actually measure this purity, we borrow a concept from information theory called entropy. Just think of it as a score for how messy or random a group is. A perfectly pure group, where everything is in the same class, has an entropy of 0. A perfectly mixed 50-50 group has an entropy of 1. The goal is always to get that entropy score as low as possible.
So how does the tree find that perfect question? It calculates which question will cause the biggest drop in entropy. And this reduction in messiness, this drop in entropy, is called information gain. The algorithm is actually pretty greedy. It looks at all the possible questions it could ask, and it always picks the one with the highest information gain to be the next split in the tree. It's just a relentless search for the most informative question.
And this slide just nails the concept. Look at the two options here. On the left, if we ask a question about account balance, we still end up with two very mixed groups. Not much help. But on the right, if we ask about employment status, boom, we create one group that's mostly green dots and another that's mostly pink crosses. The split on the right provides way more information gain because it leads to much, much purer subgroups. That's the one the tree would choose.
Okay, so we've built these really cool models. One works like a social network, the other works like a flowchart. But building them is only half the battle. How do we know if they're actually any good? Well, it's time to give them their report card.
This is really the moment of truth for anyone working with data. You can't just build a model, cross your fingers, and hope for the best. You have to test it, you have to measure it, and you have to prove that it can actually make correct predictions on new data it's never seen before.
The most basic grade you can give is accuracy. It's super simple. What percentage of the time did the model get the right answer? If it made 100 predictions and 95 of them were correct, your accuracy is 95%. It's a great place to start, but as we're about to see, accuracy doesn't always tell the whole story.
And that's where something like precision comes in. Precision asks a very specific question. Of all the times the model predicted yes, how often was it actually right? This is absolutely critical for something like a spam filter. You need that filter to be very precise, because the cost of a false positive, mistakenly flagging an important email from your boss as spam, is super high. And then, on the flip side, you have recall. Recall asks a totally different question. Of all the yes cases that were actually out there, how many did our model manage to find? This is vital for something like fraud detection. You would much rather get a few false alarms than miss even a single real fraudulent charge. Here, a false negative, missing a real case, is the absolute disaster you have to avoid.
So when you put it all together, from neighbors to flowcharts, from purity to precision, what you get is this incredible toolkit. Classification gives us a way to learn from the data we already have, to build a model that can make intelligent, informed predictions about the future.
So, we've covered the basics, from the lazy KNN to the strategic decision tree. We've even learned how to grade them with accuracy, precision, and recall. We've seen how this tech is already shaping our world in ways we don't even see. So now the real question is, what's next? Knowing this, having this power to predict, what problem would you solve? What would you teach a computer to classify?